Picture this. You board a spacecraft today. You take off, and you travel at 99% the speed of light. To you, it just feels like 5 short years have passed. But when you finally return to Earth, a completely horrifying reality sets in. 50 years have passed for everyone you left behind. Your friends, they're elderly. Your own children are actually older than you are. Look, this isn't science fiction. This is real, verifiable physics. Welcome to The Explainer. So whether you're hanging out near a black hole, where literally 1 hour equals 7 years, or you're traveling on some hyper-fast ship, the cosmos operates on this terrifying truth. Time is not a fixed, universal clock that ticks the exact same way for everyone. Einstein actually proved that time passes at entirely different rates, completely depending on how fast you're moving and the gravity surrounding you. This whole realization actually started way back in the spring of 1905. Picture a young Albert Einstein sitting on a tram car in Bern, Switzerland, just looking back at a clock tower after a long day of work. He had this wild thought. He realized that if he were to somehow speed away from that tower at the exact speed of light, the hands of the clock would appear completely frozen in place to him, right? But they'd still be ticking normally for everyone else back in the city. And that mind-bending thought right there, that birthed special relativity. The fundamental rule is this: the faster you travel through space, the slower you travel through time. If you move at 99% the speed of light, your watch is going to tick 7 times slower than a stationary observer's watch. And if you push that speed to 99.9999% the speed of light, your clock ticks an astonishing 700 times slower. It's just wild to think about. This right here is the absolute heart of the famous twin paradox. Think about it. If you stay on Earth and your twin travels out into space near light speed, they are going to return decades younger than you. And you know what the truly crazy part is? Both of you are entirely correct. Time itself physically, literally passed differently for each of you. Now, to grasp why this happens, we have to look at an impossible contradiction. See, for centuries, Isaac Newton's laws told us that speed depends on your perspective. You know, a train zooming past you looks super fast, but if you're riding on it, it feels normal. But here's the catch. The universe absolutely does not play by those rules when it comes to the speed of light. The speed of an electromagnetic wave, like light, is absolutely, completely fixed. It always travels at an exorbitant 299,792,458 meters per second. Always. It doesn't matter who's looking at it, and it doesn't matter how fast you are moving. If you fly toward a beam of light, it hits you at that exact speed. If you speed away, it still catches you at that exact speed. Let's do a quick thought experiment. Put yourself on a train platform. You're standing perfectly still. Suddenly, bam, 2 lightning bolts strike the ground at the exact same time, equal distances on your left and your right. Because you're dead center, the light from both of those strikes reaches your eyes at the exact same moment. But now imagine you are whizzing past that exact same platform on a train moving at near the speed of light. If light acted like everything else in our everyday logic, you on the moving train would run into the light ray from the front, strike way before the light ray from the back strike caught up to you, right? So you wouldn't see the lightning strike simultaneously at all. But remember, the speed of light cannot change. It must remain constant. And this right here forces an impossible dilemma. So how do we solve it? Well, the only way these two realities can coexist is through a mind-bending tweak to reality itself. To make absolutely sure that the speed of light remains perfectly constant for both you on the moving train and the person standing on the platform, the difference has to be absorbed by time. Time itself literally has to slow down for you on the train. To compensate for your extreme speed, your biological clock, your pocket watch, your very reality, it all just ticks slower. It turns out time is totally malleable. It stretches and it contracts based on your velocity. Because of this, Einstein realized that space and time were actually one and the same thing. Together, they form this single 4-dimensional fabric where every single event in the universe happens. We call it the space-time continuum. I want you to imagine this 4-dimensional fabric like a giant trampoline, okay? If you place a really heavy bowling ball in the center, think of that as our sun, it creates this massive, deep dip in the fabric. Then if you place a little marble, like Earth, on the edge, it immediately wants to roll down into that steep valley. You are pinned to the ground right now simply because the distorted fabric of space, completely warped by Earth's mass, is quite literally pushing you down from above. And because gravity gets stronger the deeper you go into that well, time actually passes measurably faster on the top floor of a tall skyscraper than it does down in the basement. And no, this isn't just some wild theory. It has been physically undeniably confirmed using highly sensitive atomic clocks. It all boils down to this. The stronger the gravitational field, the slower time passes. Just like traveling at an extreme speed stretches out the seconds ticking on your watch, a severe gravitational pull fundamentally drags the passage of time to an absolute crawl. Let's take it to the extreme. If you're near a black hole's event horizon, time passes so significantly slower that you would age at a mere fraction of the rate of someone out in open space. What feels like just a normal hour to you near that crushing gravitational well, that is literally a lifetime for the rest of the universe. Okay, so to truly visualize why gravity and speed mechanically stretch reality like this, let's strip timekeeping down to its absolute, most basic form. We call it the photon clock. Imagine two parallel mirrors facing each other. A single particle of light, a photon, bounces up and down between them. Every single time the photon hits a mirror, click, 1 second passes. It's a completely flawless, perfect mechanism. Now, imagine you're standing on top of a small hill here on Earth. Way above you, just floating in the minimal gravity of space, is a spaceship. Suddenly, one of those photon clocks falls from space. It plummets past the spaceship, and then it plummets past you on the hill. Because Earth's gravity is accelerating it as it falls, the clock is moving way faster when it zips past you than it was when it passed the ship. As that clock falls past you, you'll notice the photon isn't just bouncing straight up and down anymore from your perspective. Because the clock itself is moving downward so incredibly fast, the light actually has to travel on a diagonal path to hit those moving mirrors. To you, it looks like the light is tracing these long, stretched-out triangles. And since the speed of light absolutely cannot change, and the distance it has to travel along those diagonal paths is longer, the actual duration of a single second physically stretches out to make up for it. Which brings us to the shocking, real-world proof that you literally use every single day, GPS satellites. Because they are orbiting at incredible speeds, special relativity actually slows their onboard clocks down. But wait, because they're floating high above Earth's gravity, general relativity speeds their clocks back up. If we didn't use constant mathematical corrections for both types of time dilation, GPS navigation would drift off by about 10 kilometers every single day. Every time you open Google Maps, Einstein's equations are just silently running in the background, keeping you on track. But listen, this isn't just about satellites or some abstract physics equations. Time dilation affects absolutely every single mechanism in the known universe. It dictates the rhythm of chemical reactions, it dictates the exact rate at which your cells duplicate, deteriorate, and eventually die. It dictates you. And that leaves us with the deepest, most unsettling implication of all. You are not moving through time at the same rate as the person sitting right next to you. Because Earth's gravity is ever so slightly stronger down by your feet, your head is literally, physically, aging faster than your feet. Time dilation is not some distant theoretical concept happening out in the cosmos. It is happening to you, right now, in this exact moment.